Thanks everyone for coming. So this talk is actually going to be somewhat complementary to Shah. So in Snark, when you want to prove some argument, you can actually compute a sum check, or you compute a quotient polynomial using a quotient argument. So, surprisingly, we are also going to address in this talk some memory bottlenecks that appear in Halo2. Okay, so I'm Karthik. I'm a researcher at Ingonyama. We work on hardware acceleration, and so that's why we are focusing on memory bottlenecks and so on. So this work is based on this paper, which I wrote with Roman and Guy from Ingonyama, and you can download this paper from this link. Let me begin by just giving an outline. So I'm going to start with a quick introduction to Halo2. How many of you here are familiar with Halo2? Okay, great. So, and I'm just going to then make it sort of brief and mostly try to address it from the point of view of how the computational data dependencies appear in Halo2. And then we have two solutions which are based on graph ideas, which you can use to identify structures for computation, basically for computing the quotient polynomial. And these are connected components and community detection. And then we're going to apply these ideas to some ZKEVM circuits, because these memory bottlenecks are usually a problem only when the circuits are really huge. For example, there are like many columns in your Halo2 trace table, like 600, 700, and of that order. For smaller circuits, this is not going to be so relevant. You will have to think of other ideas like hard coding the computation yourself and use things like cache skipping. Okay, and so let me go ahead. So we're going to start with the Halo2. Halo2 is a ZKP system that uses a Plonkish arithmetization, which means we have the circuit data, which is encoded in a trace table. So in Halo2, the public data, which is the data about the circuits, the constraints, are encoded in the instance, fixed, and selector columns. And the private data, which is generated by the prover for circuit satisfiability, is encoded in the advice columns. And the idea is that circuit constraints are converted to polynomial identities, and then you prove them using the quotient argument. So basically, you can have circuit constraints like where each row represents a gate, and the wiring is the relationship between different pixels in the trace table. And you also have lookups, and all of these can be expressed in terms of some constraints, and we convert them to polynomial identities. And before we do any computation of the quotient, we're going to have to first commit to the witness, basically commit to the trace table. And commitment basically uses multiscalar multiplication, elliptic curve, field arithmetic, and all of this. And the reason I want to mention this here is that this is a universal primitive. It doesn't really depend on the circuit. And most of these algorithms have been killed to death now. So we don't really think it's much of a problem. So in general, these are very good GPU problems. You can feed it in the GPU, do a lot of parallel compute, and you can get pretty good results even with just simple naive drop-in replacement of the commitments. So by the way, this logo is for the Icicle GPU library, which was developed by Ingonyama. It's open source, so feel free to try it out yourself or reach out to us if you want something. So basically, the MSM-based compute primitives are highly parallelizable. But on the other hand, the quotient polynomial is a sort of a varied quantity. It depends on which circuit you are using. It could be compute bound and memory bound, depending on which kind of circuit, how you are optimizing, how you are calculating the circuits, and so on and so forth. The main bottleneck there is number theoretic transforms, and it uses mostly scalar field arithmetic. And the big problem is that this is not universal. So, and as a hardware company, we want to look at things which are universal, so you can build effective solutions. And the goal here is to see if there are ways we can come up with to somehow use the structure which is built in Blankish arithmetization, but somehow find a way without breaking the definition, but sort of work with it, work around it somehow, and break this data flow dependency. So how this data flow dependency appears in Halo 2 is in Planck you have these columns and trays which have 3 different constraints: gate, permutations, and lookups. So these constraints are mathematically independent but highly data flow dependent, meaning the same data is copied to evaluate different types of constraints. So the issue is, of course, the columns that you saw in the trace table have to be extended several times to several degrees for each of these constraints, and the columns may be repeating across the constraints, and you have to decide, oh, should I recompute, should I store, and it's not something that you can do very easily. Okay? So it's hard to make universal agnostic optimizations for constraint evaluation. And roughly the quotient polynomial for very large circuits like ZKEVMs and popular ZKML models is 30 to 40%. And most of the time it's memory bottleneck, as in like we have to read from host to device, which we try to avoid as much as possible. Because this, even if your compute is really, really fast, host to device data transfer basically kills the performance entirely. So we want to avoid this. And the question of when, where, and how to extend is the key to minimize the number and size of the Fourier transforms. And so just, I'm going to do a very quick run through of how do you evaluate a constraint. So let's take a sample polynomial here. So here you have a polynomial. I've not put the a1 of x. Each of it's a function of some x. It's a polynomial. And it's like degree 3. The highest variables which have a1, f3, a3. And let's represent them in terms of these blobs, which are columns. And we're going to use a degree cluster method where you're going to basically divide the expression in terms of the degree of the terms that appear. So you have degree 1 terms, you have degree 2 terms, and you have degree 3 terms, right? So the idea is that, like, what if you try to do the evaluation in the following stupid way, which is that, like, you try to take, oh, I will do degree 1, degree 2, and degree 3 in some way. What's the big advantage here? The thing is that, like, you can do coset entities. You never have to do large entities. You can do small entities of several cosets, and each coset can be done independently. So all of these red blobs here are independent fixed size entities which you can run in parallel, and this is good for GPU, right? But now you see that between one cluster and another cluster, there are like overlapping columns. And then you have this question, should I copy or should I recompute? So the blue blob here represents the one which are copied. And here in this particular diagram, you see that like you have some kind of dependency across different clusters. And you can't essentially compute them independently if you don't want to copy, right? If you don't want to copy, you either recompute or you wait for the cluster to finish, then you copy, and then you go on. So this is called cluster interdependency. And this kind of makes it very difficult to parallelize. So this is like a toy version of the problem that you actually face in evaluating the quotient polynomial. You have to constantly make these decisions, and it's not very easy to do it. Anyway, in the end, whatever way you do evaluate, you will have to extend the polynomial to the maximum degree so that you can compute the final result. Okay, so the question is how to parallelize. So the idea is that a relationship between columns and constraint is like a graph relation between nodes and edges, right? And Halo 2 already uses some symbolic representation of constraints in an abstract syntax tree. So for a simple multiplication gate like this, you have some AST which tells you how the relationship between the prover computed data, which is LHS, RHS, and out, is actually following some sequence. You can actually lift it out directly from the dev part in Halo 2. Our idea is not to actually use the AST graph, but it was more like we inspired by this idea. We want to extend this idea to use partition methods, which are available in graph theory, and to see which circuit is parallelizable, which circuit is not parallelizable, and questions like that. So the criteria that we use is connected components. It's something extensively used in data science and machine learning, and it's, we thought that, okay, well, let's try it out and see what happens. And the other idea is to find communities, which are weakly connected groups, And the idea is to see if we can use these techniques to find parallelizability criteria. So it's more like an exploratory, observatory idea, and never use these kind of tricks at the level of constraints, because if you try to take the constraints and do these kind of tricks, then you will introduce bugs, because each time you break a constraint or slice a constraint, you have to put some kind of a condition for separating the constraint. So most of the talk is that we're going to sort of apply these ideas after the prover has committed to the data. So we have the relationship between columns and constraints, which we know from the AST, but we use it at the quotient polynomial evaluation level. And then at the polynomial level, you can do whatever you want. You can separate, add, do everything, because the prover already sort of, prover already committed to the witness data. Okay, so let's start with the connected components. So what are connected components in a graph? So let's represent a graph as a tuple. We have a vertex and an edge. And this is, for example, a simple graph. So you have a bunch of vertices and some edges. And this is a multigraph when there are loops between the same. In this talk and also in general in this exploration, multigraphs are a bit complicated to deal with. So what we will do is always collapse a multigraph to a simple graph, is that whenever there are loops, we'll collapse all the edges to a single edge. And what is a connected component? It's sort of intuitive here. So if you take the simple graph here, it's basically disjoint pieces in a graph. So a connected component is a connected subgraph, which is part of a very large graph. So you have an imagination, in your imagination you have a very large graph, and you're looking for small connected components which are disjoint from other. Okay? So these are connected components. And but in order to build a graph, you need some kind of a heuristic. You have to define some rules, and these rules are not something universal. You can come up with some heuristic which works, another heuristic which will not work. And we want to go through this because what I'm going to say is not going to work, and that will give you an idea of what you should do in order to make it work. So the heuristic is the following. So we're going to define all the columns in the trace table as vertices. And then we are going to define primary monomials, which are just functions of these vertices. Basically, simple, if you have a column which has A, B, and C, and you want to compute an expression A, B, C, for example, that would be an example of a primary monomial. And then you can also have secondary monomials, which are functions of the primary monomials as well as the columns. So you can keep on going in a sequential way and build a lot of such sets and subsets and so on. But for this talk, this is sufficient. And then whenever there is a connection between different sets, you add a sort of an edge between these two things. And you can easily do it using some standard algorithm like BFS. And it's very easy to build these connected components in general. So let's see an example of the connected components and go to the same bad example that we saw before. So let's represent the columns. The primary monomials. So the primary monomials are just simple functions of the columns there. And then you have the secondary monomials, which are functions of primary monomials and the columns. So what this shows is that, like in this simple example, it basically breaks off into two connected components. And as you can see, there is one element in the first connected components and 8 elements in the second connected component. And the highest degree of the second connected component is 4, because in entity we always extend to powers of 2. So even though you have only 3 polynomials here, so it's degree 3, and I just make it degree 4. So what's the main idea here? So for each element inside a connected component, only do entity to the maximum degree of the connected component. So it, of course, presumes that there are many disjoint connected components. Otherwise, this is not very useful. And you will see what happens. I'll give you a result of what happens when we applied it to some transaction circuit in the next slide. And what is important for me is, if there are disjoint connected components, then you can do parallel compute. This is what I'm looking for. Can I get disjoint connected components? Is it even possible? Okay. So let's look at this example that we saw before. And basically, you see that this copy structure that you sometimes find by manually trying to do things will just pop out, right, if you just apply connected components. Okay, you know which part you have a problem with, which part you may need to rewrite the circuit, rewrite the constraint, whatever you want. So you can use this as an analytic tool to say, okay, you know what, should I optimize my circuit differently in order to get my desired result? Okay, so basically it identifies independently computable connected expressions. This is my main interest here. As I said before, several disjoint connected sets enhances parallelizability. So we applied it to this transaction circuit in PSE, and we find that there are two bunches of connected components. But if you apply it to some big circuit like ZKEVM, you see this. Everything becomes one big family here, right? So it's not very good for, that sees that this idea is a problem. And what's the problem is that when you have permutations and lookups, high circuit interconnectivity, this kind of increases the data flow dependency and things that you need to copy. And of course, this is kind of obvious. We are building big circuits, right? You're going to have this problem. So maybe we are just looking at it a little bit wrong. Maybe we shouldn't look for completely disconnected pieces. Maybe we should look for weakly connected pieces, right? And that's the whole idea of community detection. And this idea is well known. It's been there for a long time. People have been studying it in network theory and so on and so forth. And so let's define what a community is. The thing is, there is no good definition. It's just sort of very heuristic. So in thing that works for me is that like you have a bunch of a graph which is split into k groups. And in each group, the intra-group edges are very dense, basically strongly connected components. And the intergroup edges are sparse. So the edges that go between one connected component to the other are few, right? So this is what we are looking for, and this is my definition of a community. So basically, community is a bunch of weakly connected groups, and each group is a strongly connected component. So these are all strongly connected, but these and these are weakly connected. Okay? Again, you can find this. This is an NP-hard problem. Don't try to do something. You're not guaranteed to get anything. So there are many heuristic solutions. You have modularity of partition. You have edge betweenness, Girvan-Newman algorithm. And you have max flow min cut, which is one of the more stronger algorithms. So in this talk, I'm going to only focus on edge betweenness and Girvan-Newman because it's very physically intuitive. But you can use any method. It doesn't really matter. So choose your favorite community detection method, and you might get something good out of it. So this Girvan-Newman algorithm is found in this physics paper. I was a former physicist, so I had to put this here. This has about 17,000 citations, only 2,000 citations lower than the famous ADS-CFT paper in string theory, if there are any string theorists in the audience. So basically in Girvan-Newman, you compute something called the edge betweenness centrality. So the edges that connect communities have high betweenness. And what's the meaning of this betweenness? Is given an edge, and you're going to compute the number of shortest paths in a graph that include this particular edge. And then you're going to count the number of shortest paths between the same pairs of edges. And then you're going to sum over all possible edges. Okay? So let's look at a simple example. Here is a very symmetric graph. So you can pick any pair of edges and ask how many of these paths actually pass through the edge CD, right? So this graph, the denominator function is always 1, because if you take any pair of edges, there is just exactly one shortest path. But if you ask what's the shortest path between any pair of edges that will always contain this edge, then the answer is given here. Okay? It's sort of intuitive. If you start from BFS and start evaluating the shortest paths, you will see that like this is sort of symmetric about this point. And so this path, every path that has to pass through will essentially have to pass through this. So the idea of community detection is that high traffic edges, if you peel them off in a graph, then you get community structure. Okay, so this is our idea. Basically, like, you just know that this exists. It's been applied always in network theory. We'll just use it to make polynomial evaluation easier, right? So recursive application, you can do this, but it will sort of only split a graph into a subgraph and subgraph into subgraphs, and the end result is like a tree, right? So this was written in, it was surprisingly, I didn't find it in Rust. So Roman wrote a code which is available in PetGraph library. So you can use this if you want to play around with it. And so we have to build the graph. So we have to define some heuristic. And this time I had a problem. Like I didn't want to complicate matters too much because it's very heuristic and it runs for a long time. So I defined it for only columns. So this time the relationship graph is built simply between columns. No sub-expressions, no monomials, no nothing. So, and then we're going to just see which edges are connecting which columns. So we'll make an edge with the following criteria. And this is very heuristic. There is no universal criteria here. And my heuristic is that I'm going to put an edge between two vertices if they belong to the same custom gate, the same permutation set, or the same lookup argument. Okay? It's a very simple heuristic. And you can easily build the theory behind it. And the idea is that you apply the Girvan-Newman algorithm, and it will cluster all the columns in the trace table in terms of different connected components. So each of this is just a bunch of vertices. Okay? So this is what the Girvan-Newman algorithm does. And then it will create these high traffic edges, which basically connect across different columns. Okay? So that's the result of the Girvan-Newman algorithm. And basically it contains a subset of columns. And the idea is to minimize the number of high traffic edges. Okay? The idea is to somehow minimize the number of high traffic edges so that different connected components that are appearing in the Girvan-Newman algorithm have fewer edges that are overlapping across them. So, of course, we want to do a sort of simple split, not to do many connected components. So we use some kind of greedy algorithm. And the idea was that like to take a large circuit and to split it into two approximately memory-wise even parts so that we can have them almost to be of the similar size. Imagine you have a GPU of 20 gigabytes memory and you want to use a smaller GPU which has only 10 gigabytes memory, and you can use two of them because they are cheaper or whatever. So you can try to split it in some way, right? That was the kind of intuition. So I define a good two-way split is if the largest community in the Girvan-Newman algorithm is like 50 to 60% of the total circuit size. So this is what we do. We use the greedy method of merging the smaller communities. And we assign the columns to different objects which we call bins. So we take the largest community and put it to bin 1. And then we merge the other smaller communities. And whenever there is an overlap between the two, like if you see there is an edge that connects from bin 1 to bin 2, I'm going to take the column from the largest bin and put it in the smaller bin. Okay? So this is a price that I'm paying for this separation. So that's why we want to have minimal number of copied columns so that the overhead is sort of low. And this is the optimization criteria. So for separability, you pay a price, you recompute some entities. That's basically the whole idea. And how do you evaluate this in practice? Because it's all nice in theory, right? But H-poly code is a mess. So we sort of had to come up with some way to assign which column belongs to which bin. And you can do it using a simple Boolean vector. Say that in bin 1, you have this lookup, this permutation, this custom gate computation. And in bin 2, you can have the same thing, but also they can appear in different terms of the H-poly, right? In quotient polynomial, you can have a custom gate. Part of it comes from bin 1, and part of it comes from bin 2. You can have things like that. So the main idea is to somehow use this to wrap it inside the quotient polynomial evaluation code. And what you see is that like you can put a simple for loop that runs over the different bins. So this means you can actually evaluate each part of the quotient polynomial separately as two completely independent expressions. Ideally, you would want to do it at the circuit level, but this is very complicated and it introduces bugs. So in quotient polynomial, at least it's clean in terms of theory, very dirty in terms of engineering. Okay? So this is the problem. The main problem is that every constraint is linearly independent. So there are powers of y, and part of it will, Part of it is evaluated in one bin, and part of it is evaluated in another bin, and both of them has the same power of y. So if a given constraint, part A is coming from one, and part B is coming from another, you will have to use the same powers that make the linear independence on both, and you have to keep track of it using some indexing. So the whole thing is an indexing nightmare. Theory-wise, it's very simple, but engineering-wise, it took several hours, weeks, even months to get the correctness right. So bottom line is this. So Girvan-Newman gives you, takes the graph and split it into bin 1, bin 2, and some edges to copy. So the effect is you take the trace, you split it into two parts, and you pay a price by copying some of the columns across. Okay? Yeah. So essentially, the quotient polynomial in bin 1 and bin 2 can be run independently in parallel. And the goal is somehow to keep these copied columns small. So you can pay a small price for parallelizability. And I'll show you in an example where it actually is beneficial. So essentially, we can solve memory bottlenecks by splitting the trace. And the trade-off space, as I said, is to recompute small number of entities. And if you can afford it, it's a good trade-off. Okay? So let's apply it to some ZKEVM circuits. We first applied it to Taiko ZKEVM because it's a sort of a medium-sized in terms of ZKEVM standards. So you have given partition on this, and we got 2 connected components. So you can see one of them has about 300 columns, another has about 250 columns, and with an overlap of about 23. So we try to, you can represent the graph in terms of some, so the blobs that you see, the black ones are actually the actual columns, and there are many, many edges. And as you can see intuitively from the graph, you have some kind of rough partition that you can create. And the largest community is like 50% of the total community size, which is good. And so we sort of ran this in CPU. There's no GPU implementation of this yet. It's a proof of concept. So what you see at the base level, you have a total instance size of 20 gigabytes. And in splitting it into 2, you roughly split it in 10 gigabytes each. Okay? And so it solves the memory bottleneck. And in addition, you see that the latency of the full runtime is reduced to the latency of the largest community. Okay? This for me is actually good because then the combination is not so much of a problem because you essentially do field additions in the last part of merging the quotient polynomial. So that's okay. So that's not so much of a problem. So the difficult part was reproducing that the results produce the naive quotient polynomial entirely. So it's an engineering optimization without doing any cryptographic change. But the idea of separability we essentially took from the graph theories ideas and applied it to this. So now let's apply to another ZKEVM circuit and see if we can reproduce it all over the place. And then we find that it's problematic. So we applied it to scroll ZKEVM. And we find that the split is like 68% of the total circuit size. So there was no efficient way to partition this. So the largest community is about 658 columns. And if you try to recursively apply this Girvan-Newman, it takes the 658 columns and split it into 564 and 94 and increases the number of edges you want to copy. So the more you apply and more you partition, the more price you pay for copying and recomputing, which we don't want to do. So I decided, okay, so the whole thing is about finding the largest community. If you find a large community which is like 50 to 60%, you're good. And if not, maybe you want to rewrite your circuit or do some other optimization and so on and so forth. And the main reason for this is, again, you have about 190 columns of permutation which participate in a permutation set in scroll. And this is from an old data, so things keep changing in this. And by the time we finish getting correctness for the H-poly nightmare, circuit might have changed a little bit, so there may be some changes. But to just give you a comparison, in Taiko, there were about 15 permutation columns, and this is 190. So that's what actually causes this whole thing to become connected. But you can try different graph heuristic methods, maybe define your own heuristic, explore a little bit, experiment with max flow, min cut, and different algorithms, and you might get slightly different results. Okay? But I think the general idea of Girvan-Newman is pretty to understand the intuitive structure of circuit. You know what, for example, by plotting it in this form, I can even tell you what part of a circuit is. For example, you see this triangle here, that's the pi circuit. And these snowflake thingies here, they are from transaction circuit. And somehow there is some kind of topology there, and it's visible inside the graphs. Just need to know how to represent it or how to visualize it, and you have some way of understanding circuits in a different dimension. So I think it's pretty cool. So I think that's it. I'm going to summarize. So we applied graph methods, and we tried to use connected components. And the main takeaway from connected components is you only need to compute Fourier transforms, which is of the largest degree in the CC set. If you get many disjoint CC set, you can parallelize, but it rarely happens in ZK circuits. So I think the more practical direction is to do community detection. And we applied Girvan-Newman. You can apply any algorithm that you like, but you should try different methods, and there may be some trade-offs. And essentially, if your definition of circuit has large permutations, you will have less parallelizability. But maybe there are ways around this. So we try to apply it to ZKEVM circuits like Taiko and Scroll, and we find that for Taiko, at least, we have a pretty good split. And we can solve memory bottlenecks. So that's it. Thank you. I'm going to leave you with this discussion slide. If you have any questions, feel free to.
One quick question.
Yeah.
Hi, thanks for the talk. It's very good. So this seems most immediately useful as a way to figure out how to parallelize VMs that were not necessarily written with parallelization in mind.
Yeah.
That being said, have you thought about, like, now that we know how to do this kind of thing, how would you design a VM custom made to like really lean into this technique?
Yeah, actually, it's a great question. Actually, that's the direction that we are sort of trying to think if we can do stuff. And I started by trying to apply it to witness generation. But it's very, very hard. Usually, everything becomes one big graph of connected components. And I don't know if there is a way to do it, but VMs, and I'm like looking at RISC-0, for example, they have announced in their performance that they have found ways to chunk parts of the code, and witness generation for these parts itself is parallel. In GNARC, for example, they find, in GNARC Plonk, they find actually like streams which are like, it's like the compiler fires and finds that, okay, these constraints can be evaluated, these constraints can be evaluated, and it does in parallel if it is possible. But it's not like in the main code, it's just a sort of a, but in general, yeah, this is the direction that I think we need to do some research. And the idea was to see if we could combine with Tushar's streaming algorithm somehow, if you could identify chunks in circuit and prove these chunks, and then somehow try to combine them in a nice way. But yeah, this is the direction that I would like to take it in general. Yeah.
Cool, thank you.